Hi everyone, and welcome to our lesson on projectile motion. Now this is one of my favourite topics because projectile motion is something that comes naturally to most people. Most people understand that when you throw a ball, it behaves in a predictable way. And if that wasn't the case, then baseball would be a very different game because every time you threw a ball, you wouldn't know what is going to happen. So the study of projectile motion seeks to explain and quantify how a projectile, a ball or a particle, moves through space. So to understand this, first we have to understand what a velocity is and what a force is. And a force is something that accelerates an object. A force is something that changes the velocity of an object. So a ball in flight can be under either ideal conditions or real conditions in reality. Here's what the ideal conditions of a ball in flight is. There is the ball. We'll say that is the velocity, and the force acting on the ball acts directly downwards towards the ground with mg, the weight force. However, in reality, the ball does not exist in a vacuum, so we have a few forces. Here's the velocity. Now the velocity is not a force, but I'm marking it in. There is the weight force, mg, and then we have air resistance. And air resistance acts in the opposite direction to the velocity. So the air resistance acts in this direction here. Force, we'll say resistance there. So the net force on this ball here is the same as the gravity force. But in this picture, the net force is what you get when you add up this little arrow to this arrow. So it is somewhere down here. And the net force on this ball actually slows it down horizontally. So the path of an ideal ball is a perfect parabola, and the path of a ball flying through the air in reality looks something like this. This is what you might expect if you threw a ball bearing through the air, and this is what you'd expect if you threw a shuttlecock through the air, depending on how much the air resistance comes into it. So first of all, let's look at how a projectile in motion has both horizontal and vertical components to its velocity. Here's the projectile, and here is its velocity. Let's say that velocity acts at an angle of 30 degrees to the horizontal. Now I'll mark in red the horizontal, and I'll mark in yellow the vertical components to this velocity. So the horizontal is given by this line here, and the vertical component is given by this line here. And it's effectively two different vectors, the red and the yellow, but when you add them together you get the true the velocity you'd see in real life. It's important to divide up the velocity here into these two vectors, so that way we can see how forces affect them. Okay, so we ask ourselves, what is the relationship between this magnitude v and the horizontal vector here? Well, we know it's a triangle. This side has length v, and we'll call this side length vh. So vh is different to v, and the opposite side v vertical. So according to the trigonometry, cos 30 degrees of any triangle equals the adjacent over the hypotenuse. In this case, that's vh over v. Therefore, velocity, multiplying this into here, times cos 30 equals vh. So the horizontal component of the velocity of this projectile is v cos 30. And we can use the same reasoning to find the vertical component of this velocity. We have a triangle, so sine 30 degrees is equal to the opposite over the hypotenuse, which is equal to v vertical over v here. Therefore, multiplying both sides by v, v sine 30 degrees equals v vertical. And the reason this is very, very useful is as follows. The weight force in ideal conditions acts directly downwards, and the force seeks to change the velocity of an object. It seeks to accelerate an object. If a force acts in this direction, and there is a horizontal component of velocity acting at right angles to it, this force will never change the horizontal component of this particle's velocity. It simply cannot change it. It will, however, change the vertical component of the velocity. So once we've separated these two things out, we can work out things like how long it'll take for a ball to reach maximum height. So say v was equal to 10 meters per second. Then v vertical, the vertical velocity, is equal to 10 sine 30 degrees, which is equal to 10 times a half, which is 5 meters per second. And everything under the force of gravity is being acted on by force mg, and if the particle is mass m, well, that means the acceleration is negative 10 meters a second there. So a equals negative 10 meters per second squared. So using a quick motion formula, v equals u plus at. At the max height, v will be 0. U is equal to 5 meters a second. A is equal to negative 10. And then t is the one we want to find. 5 over 10 equals t. T equals 0.5 seconds. If we'd accidentally applied 10 as the initial velocity here, as some people do, we would have got completely the wrong answer. So the reason we choose to divide up a projectile's velocity into horizontal and vertical components is so we can tell exactly how the gravity force, or indeed any other force, acts on it. For more difficult projectile motion questions, look towards the next few videos.